Thanks everyone for coming. Let me thank the organizers for this opportunity. And today I'll tell you about device-independent uncertainty for binary observables. Can you hear me now? Hello? 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 Can you hear me? Oh, thank you. Cool. So device-independent uncertainty for binary observables, and this is joint work with Marco and Stephanie. Okay, the outline of the talk. First I'll give you a mini framework for uncertainty relations, and this is just kind of to figure out what is an uncertainty relation. Then I'll tell you about binary observables and why anticommutation is an interesting feature for these guys. And then I'll tell you about partial anticommutation, what it means and how you can get entropic uncertainty out of that. So this is somehow the technical part of the talk. And then as a summary, I'll give you a very simple procedure for device-independent uncertainty based on these techniques, and I'll end the talk with two interesting open questions. Okay. Uncertainty relations. Before I go into the mini framework, I'll just show you a couple of examples, which I'm sure you all know. So we have the Heisenberg one, which relates the standard deviations of the position and momentum operators. We know that this can be generalized to arbitrary observables. So now the quantity on the right-hand side actually depends on these observables and the state. And this is also a modern example of an uncertainty relation. So you have entropies on the left, and you have the overlap on the right, and somehow the overlap is the modern measure of incompatibility. And obviously there are many more. Every week on the archive there is at least one paper that finds a new uncertainty relation. So then you look at them, and at first glance they seem kind of completely unrelated statements. So how do we put them all under kind of the same umbrella? And what is the usual setting for an uncertainty relation? Usually you start with a state, and you have a measurement, and you can perform the measurement on a state, and you get some classical outcome. And maybe there is another measurement you can do, and you get a different classical outcome. And in principle, there could be many measurements. And you got all these interesting books, and you can read them, and you find them useful. But at some point, there's somebody who's going to come and say, look, I'm not even going to look at these books because they are, it's just random junk. I can guarantee that this is all random junk. And you say, well, how can you say that? You haven't even looked at them. And he says, well, but I know quantum mechanics. So if I know something about the state and the measurements, I can predict something about the outcomes. And at least for me, this is essentially what an uncertainty relation is. Any mathematical statement that relates the properties of the state and the measurements with the somehow non-determinism or uncertainty or randomness of the outcomes, is an uncertainty relation. So how do you make it rigorous? We need three components. We need a measure of incompatibility, which is a function of the state and the measurements. We need a measure of uncertainty, which depends only on the outcomes, and we need a non-trivial relation between the two. So somehow if somebody promises you, there is certain incompatibility in your state and measurements, then this gives you a lower bound on the uncertainty. And so in a way we're looking for these trade-offs, and there is one danger. For any two pair of measures, this trade-off is kind of well defined, and you can find it by solving this somehow contrived optimization problem in which you say, okay, let me fix my measure of incompatibility, and let me just minimize uncertainty over all possible realizations, all possible quantum systems. And clearly, if there are so many of these trade-offs, it cannot be the case that all of them are interesting. I mean, that would be just kind of too many interesting objects. So then you ask, okay, which ones are interesting? Like, what do we want? What kind of statements would we find kind of useful and interesting? And this is kind of purely subjective, but I think most people would agree that the measure of incompatibility should be a simple function of the state and the measurements, should be kind of easy to verify. So if somebody gives me a device, I should be kind of able to verify it, ideally in a device-independent fashion. The measure of uncertainty, well, ideally it would correspond to some kind of operational task. So then you start thinking about entropies, because we know that these quantities have operational significance. And then the relation between the two should be a kind of a simple mathematical, you should have a simple mathematical formulation. So you should be able to kind of write it down with not too many symbols. And so, okay, so so this is kind of what we want. This is what we're after. And the object we study in this work is a set of multiple binary measurements. So when I say multiple, I mean more than two. And when I say binary, I mean with two outcomes. And note that the usual kind of uncertainty setting, the usual kind of uncertainty papers only consider two measurements. And for these, you have this Jordan's lemma that allows you to do dimension reduction, and you look at qubits, And for qubits, the problem is much simpler. So somehow, since we want to deal with more than 2 measurements, we don't have this tool. And also because we want to base our uncertainty on something that's kind of device independent, we don't want to make any assumptions on the dimension. So somehow the space we're looking at is quite big. And know that the very, very special family of binary observables has been studied before by Stephanie and Andreas. And these are observables which are somehow pairwise maximally incompatible. And I'll tell you exactly what it means. And really the question is, can we provide a generalized statement that applies to an arbitrary set of binary observables? Okay, what is a binary observable? Well, a binary projective observable is just a Hermitian operator that squares to identity. And if I perform this measurement on my state, I obtain a probability distribution with 2 outcomes. It's a 1-parameter family, so it's fully characterized by its expectation value, which is just a number between -1 and 1. So it's a very simple kind of setup. And at least for a qubit, we know that the intuition is the incompatible measurements, they anticommute. So if I take sigma x and sigma z, I can very easily verify that they anticommute. So somehow we think that anticommutation is a nice measure of incompatibility. And in fact, you can prove this, and this is what was done before. So if I take n binary observables and they all pairwise anticommute, so somehow they are all kind of as incompatible as they can be pairwise. And I define G to be kind of the vector of expectation values. So the jth component of this vector is the expectation value of the jth observable. Then whatever state I pick, the length of this vector is at most 1. Okay, so it's a short vector. And note that I have n observables, but the length is only 1. So the length doesn't scale with the number of observables. So this is an uncertainty relation in disguise kind of thing, because the requirement that the observables anticommute is a incompatibility statement. And then this implies this kind of spherical constraint, which is a measure of uncertainty. And actually, it's quite a strong measure of uncertainty, because you can you just do the simple calculation. If I want one of my outcomes to be deterministic, this essentially forces all the other outcomes to be uniform. Okay, so this is actually quite a strong requirement. So now the question is, okay, this is a nice statement, but it only applies to observables that exactly anticommute. So what happens if they only approximately anticommute? And then you hit the question, what does it mean to approximately anticommute? And the most natural thing is to you calculate this anticommutator, which is an operator, and then you say, okay, let me just evaluate it on my state. And this gives me a number. After normalization is between -1 and 1. And note that if the observables anticommute as operators, this number is actually always 0 for all states. So in that sense, we recover the previous case, but it kind of gives us a richer structure. And note that since we have many observables, so somehow for every pair we can calculate this number. So you have all these numbers. How do we keep track of all of them? Well, we can put them into matrix. So I define this anticommutation matrix, which has zeros on the diagonal, and then the off-diagonal elements correspond to exactly these kind of pairwise effective anticommutators. And note that if I go back to the previous case, to the kind of ideal anticommutation case, all the off-diagonals vanish, and you end up with identity matrix. So this is the case considered before. Okay, so it turns out that having defined such a matrix, we can make a very simple statement about the relation between the vector of expectation values and this matrix. And so if I give you the vector and I give you the matrix and I ask that are the two compatible, then you would just check this matrix inequality. And actually the proof is very simple. The proof is 3 lines. You really construct a gram matrix of a certain set of vectors. You realize that what appears in this matrix is exactly this vector G and the anticommutation matrix T. And you check the positive semi-definiteness condition for this matrix, and you get exactly the matrix inequality that I showed you. So the proof is very simple. You get a simple relation, and now you ask, okay, what does it actually mean? So it has a nice geometric interpretation, it turns out, because T is a positive semi-definite matrix, and it defines an ellipsoid. And this condition means that the vector has to lie inside the ellipsoid. So if I have 2 measurements, these are the kind of the allowed regions in which the vector G must lie. So for epsilon equals 0, which corresponds to the maximally incompatible observables, you get the circle. So this is kind of the two-dimensional sphere, you know. So this was kind of known before, but now I can say, okay, let me increase my epsilon, for example, set it to 1/2, and what is the allowed region now? And you realize that what you get are these kind of ellipses that, you know, are elongated along the main diagonal. And so this is kind of like a nice geometric interpretation of this condition. And the good thing is that if you want to hit the deterministic points, which are the corners of the square, then you really need your epsilon to be ±1. Or in other words, if your epsilon is not ±1, so if the modulus is strictly less than 1, there is some uncertainty. So in that sense, this analysis is kind of robust. And note that if I kind of come back to the case of T being identity, I just get the sphere again, the spherical condition. So in that sense, this is a nice generalization of the previous results. Okay, so we have uncertainty in terms of this vector of expectation values, but this is not what people are usually interested in. They want entropies, and the usual kind of entropic uncertainty relation considers the following scenario. So suppose I have n measurements, so I pick one of them uniformly at random, say 2, I perform the measurement, I get some classical outcome, and then I'm going to kind of construct this state which has 2 registers, and the first register is the outcome, and the second register is the label of my measurement. And an entropic uncertainty relation is just a lower bound on, say, some kind of conditional entropy, for example, the alpha Reni entropy of x, the outcome, conditioned on the label of the measurement. Since we have binary measurements here, so everything just depends on the expectation value, so the formulae get a bit kind of simpler. And so now you might think, okay, if I just want to find a lower bound on this, I could just minimize my entropy function over this allowed set, this kind of ellipsoid. And maybe this is a simple task, but actually it isn't. So even for the simplest case of 2 measurements on a qubit, you cannot do this analytically. Okay, so what you can do is you can consider this kind of spherical relaxation in which you take the ellipsoid, or the ellipse in this case, you kind of bloat it up into a sphere, and note that the radius of this sphere corresponds to the largest eigenvalue of the anticommutation matrix. So it's somehow nice because you've compressed all the knowledge about all these anticommutators into one number. And now you're trying to kind of optimize your entropy over, well, the sphere, but actually you cut out the bits that like stick out of the hypercube, because we know this is not allowed. So it's really the intersection of the hypercube and the sphere. And I don't have time to go through the technical details, but let me assure you that because of certain concavity convexity properties of these entropies, for most values of alpha, you can find the optimal assignment. I mean, you can find the optimal point that somehow gives you the trade-off. And then you can write a lower bound on your conditional entropy in terms of just this number r, which is the radius of the sphere, which is the norm of the anticommutation matrix. So somehow you can get a really nice kind of compact lower bound on the entropy. Okay, the question is, how good is this? I mean, we want to kind of compare it to something we know to see if our analysis is tight or maybe it's not tight at all. So we take the most kind of well-studied case of the Shannon entropy for 2 measurements, and we realize that the expression we get looks like this. So it's 1/2 of the binary entropy of something that depends on the modulus of the epsilon. But now if you want to compare it to something, since most results relate like state bounds in terms of the overlap, we say, okay, maybe we can specialize it to the case of a qubit, because for a qubit there's a simple relationship between the effective anticommutator and the overlap. And actually, that's true, but then you kind of realize that for qubits, this has already been known. So in that sense, you come up with this expression, but once you specialize it to a qubit, this was already known. You can still plot it, and you realize it's actually quite a strong bound. So in the plot, you see the solid line is the optimal value, so somehow the exact value of the optimization problem. The red dotted line is the bound that I'm talking about right now. For example, the bottom line, the blue line is the Massine-Newfing bound, so this is the very famous. The green one is a recent bound based on majorization, but somehow the bottom line of this is that the bound we're talking about right now is the best analytic bound, analytic bound that has a simple form that is known so far. So as I said, for qubit, this was known, for 2 projective measurements on a qubit, but now we show that you can actually talk about more general systems, arbitrary dimension, as long as you replace the overlap with this kind of effective anticommutator. So it's a nice measure of incompatibility. Okay, so we have this entropic uncertainty. Now, I claimed before that this can be used for some kind of device-independent purposes. And so how do we link this to device-independent? Well, so we had in the tutorial this morning that if you want to obtain a good CHSH violation, your observables should not commute, okay? So Nicolas showed us a formula in which he says, if you want a big violation, then the commutators have to be big. And you can prove a kind of conceptually similar relation, which now says, if you want a big violation, the anticommutator has to be small. So this is exactly what Marco and Esther did a couple of years ago, and you can use this to, if I observe a certain violation, this gives me an upper bound on the size of the effective anticommutator for this kind of pair of observables. And this is a nice relation because it's kind of robust. As long as I observe any violation more than 2, I get some non-trivial bound on this anticommutator. So if you combine this with the previous uncertainty analysis, you come up with a very simple certification procedure, which is based on this game proposed by Slofstra, in which for every pair of observables, you play a slightly different CHSH game. This allows you to estimate this beta jk, and I kind of implicitly make the IID assumptions. You can play this game many times, and you can get a good estimate of beta, of the violation. From there, you can calculate a bound on the effective anticommutator for every pair. Once you have that, you can calculate a bound on the norm of the anticommutator matrix, and from there, we know how to get a bound on the uncertainty, on the entropic uncertainty. And so this is a kind of a nice, neat procedure, and it's also robust in the sense that if you observe any CHSH violation in any of the games, then you will get strictly positive uncertainty. So there is no kind of threshold, any violation implies some positive uncertainty. Okay, so this leads me to final questions, a couple of open questions. So whenever somebody says, look, I've got this uncertainty relation which can be kind of certified device independently, you think, okay, can you do crypto with it? And actually we did have an application in mind, but unfortunately our application requires us to condition on additional classical information. Okay, so because we want to give the adversary the power to hold some extra knowledge. And unfortunately, our current methods do not allow us to do this extra conditioning, and there is a very kind of cute but annoying counterexample to that. So there are kind of 2 ways out of it. Either we impose some extra assumptions, and then you kind of have to argue that these assumptions are realistic or they are kind of justifiable, or maybe you just come up with an application that doesn't require this extra conditioning. So this is kind of towards how to find real applications for our kind of uncertainty results. A more theoretical line of research would be, well, this kind of anti-commutation stuff seems to work very well for binary observables. The results we get are quite tight. So now, can we do it for observables with 3 outcomes? So we know these can be represented as unitary matrices with eigenvalues which are roots of unity. And we also know that incompatible measurements, which correspond to mutually unbiased bases, are known to satisfy this kind of twisted anti-commutation relation. So rather than having a factor of -1, you get a factor of omega, which is the root of unity. So then you might think, okay, maybe we can generalize our techniques to make statements about these kind of ternary observables, and that'll be very interesting because very few things are known about these kind of uncertainty problems. So I guess with these 2 questions, I would like to leave you. Thank you very much for your attention, and I'm happy to take any questions.
What about the relation between the alpha, the order of the entropy, and your epsilon? Is that, did you have it explicitly on the slide somewhere?
I don't have it on the slide, but well, so I guess for different alphas, okay, so there are the 2 families. So there are the kind of the small alphas close to the Shannon entropy, and there are the big alphas more than 2. And the key thing is we can find the optimal assignment for each of these families, and then you just need to evaluate the correct Renyi entropy on that assignment. So in that sense, we bound this expression by some other Renyi entropy, by the same Renyi entropy, but for a different distribution. So that's gonna be your alpha dependence, if that's what you're asking, more or less.